Okay, hi everyone. Welcome to my video number 2. For this video, I'll talk on double integral over general region. Double integral over a general region. In my previous video number 1, I'll talk double integral on the rectangular region. Right now, more general region. So in this case, our Frobenius theorem, we have two types of Frobenius theorem. Frobenius theorem, we have two types, type 1 and type 2. So this let's go to the type 1 first. Type 1. For this, we assume that our region D is given as X between A and B and Y between two functions. Let's say G1 of X, G2 of X. So that is our region. So in this case, if you describe it, right, if you sketch a little bit, it look like let's say we have this function 1, function 2. So this is y equal to G1 of X, this is y equal to G2 of X, and X from A to B. This is our region D. Okay, or we can also have something like this. This is from A to B. This is y G1x, G2x. This is y G1x. So to choose which one, G1, G2, we look at G1, normally a function smaller than G2. Smaller, I mean with respect to x-axis. Yeah. Smaller with respect to x-axis. Then where G1, G2, where G1 and G2x are continuous function on AB. Yeah. Then our integration look like integration over D of xy dA. The outermost integral, we should have constant here, not a function. So in this case, we take x. We integrate respect to x for the most outer integral, and the inner integral from the smaller function to the bigger function. This is y equal to G1x to G2x. Either you want to consider like that or any form actually. F xy dy dx. Okay, let's see example. Let's say we want to evaluate that integral x plus 2y dA, where our D is given as or say D bounded by y 2x squared and y 1 plus x squared. If you sketch the region, so for y equal to 2x squared is look like something like this. Alright, this is for y equal to 2x squared. Then if you look at y, 1 plus x squared, so we have 1 here, then we have 1, let's say 1 here. So our function look like this. So this is y 1 plus x squared. Of course, you can find the intersection, line of intersection here. If you solve those two equations, you can find the line of intersection, point of intersection here, where here you got, here is -1, here is x equal to 1. So therefore, in this case, our region D is given as x between -1 and 1, and y between, the smaller one is 1 over 2x squared, the bigger one 1 plus x squared. Right. So therefore, our integral will be like integral x from -1 to 1, y from 2x squared, 1 plus x squared, 1 plus x squared, and our integrand is x plus 2y dy dx. So now we evaluate this, integrate this iteratively. So first, with respect to y, x -1 to 1. So y, we have xy plus y squared, y from 2x squared, 1 plus x squared dx. So all this thing. Alright. So this equal to x from -1 to 1. So substitute the value x1 plus x squared plus 1 plus x squared minus x 2x squared plus 2x squared. Right, so that's dx. Okay, simplify that. X -1 to 1. So here we have x plus x cubed plus 1 plus 2x squared plus x to the 4th. Here you have minus 2x cubed minus 4x dx. So if you rearrange this, -1 to 1, so I put it the less power is in front, so we have 1 plus, so you have x, then we have for x squared 1 here, so 2x squared, and x cubed, we have x cubed 2, so we have minus x cubed to the 4th, that's minus 3 x to the 4th dx. Alright, so I think I don't have to evaluate this, you can evaluate that. I just give you the answer. This will give you 32 over 15. Okay, so this is for the type 1 integral. So type 1 integral means, alright, type 1 integral means x between two constant and y between two function. For the type 2 integral, type 2, the region D is given as xy such that y between, let's say, C and D, and x between h1x, h2x. Okay, so the difference between type 1, type 2, type 1, x between constant, y between function, whereas type 2, y between constant and x between function. Okay, so if you can visualize this graphically, so it should look like something like this. Let's say we have two functions there and y between two constants. So this is y, c and d, and x, this is h1x, this is h2x, where of course we need h1x, h2x continuous on CD. So let's consider example. Find the value of, let's say we have a solid x squared plus y squared, and above the region in xy plane, bounded by y equal to 2x and y equal to x squared. So here our function or our integrand, this is our function. This is fxy. Okay, so well, I forgot to mention that normally when we deal with a function of two variables, z equal to fxy, alright, normally in this case we deal with a surface. We have a surface like that. So this is our function described by that surface, and the region down there is anywhere on xy plane. So this is our region, where this region of course bounded by whatever function given here. So in this case, if we plot or we sketch those region, remember that we just need to sketch. You don't have to sketch this function because that's a bit difficult for the moment. I just want to focus on how to sketch or to identify the region R. So for the region R, so we have y equal to 2x. You can sketch that one easily. You can see that y equal to 2x, and the other one is y equal to x squared. So also you can do this. That. So this is y equal to x squared. So you can identify the region. This is the region D. So if you solve these two equations, you can find the intersection point 0 and I think here is 2 and here is 4. Solve these two equations, then you can find those 2 and 4. Okay, so in order to evaluate this, so why do we have volume here? So if you plot in 3 dimension, so you have this y equal to x squared. This is x, y equal to x squared. So you have something like that. Another one is y equal to y, so you have something like that. So this is our region. So this is our region, and we have a surface here. Remember that we have a surface here that I mentioned earlier. So this surface bounded by that. So we have something like that. So this is our domain, our region. So we have a volume. Okay, we have a volume. So we can solve this in two ways. First, we can use the type 1, and second, we can use type 2. For type 1, for example, of course, for type 1, remember that for type 1, we have x between two constants. So we integrate x from 0 to 2, x from 0 to 2, y between two functions. So in this case, with respect to x exists, so this is y equal to x squared should be a smaller function as compared to y equal to 2x. So y equal to x squared is here is equal to x, and our function, the integrand, is the surface here. The surface here is given by that function. Okay, so we have x squared plus y squared. So we integrate with respect to dy and dx. So I think for this case, I don't have to solve in detail. You can do this. The answer is 1216 over 35. Okay. Now, if we use type 2, remember that for type 1, we use x exists as our reference axis. For type 2, we use y as our reference axis. So for type 2, the outer integral must be a constant. You cannot put a function as the outermost integral. It must be a constant. So in this case, y from 0 to, so look at this, use y axis as a reference axis. So y from 0 to 4, and x, you need to write this as a function of x, as a function of y. So x as a function of y. So in this case, you have x equal to, in this case, you have x equal to set y. Of course, we have plus minus, but minus is this side, plus is this side. So we consider the plus one. For this, the straight line here, x is equal to y over 2. So use y as a reference axis. So it seems that x equal to y over 2 is smaller than that function. So we put this as a lower bound, whereas the other one as an upper bound. So this is y over 2, and to set y, x squared plus y squared dx dy. Again, I think I don't have to solve this. I just give you the answer. We have 126 over 35. So whichever you do first, either that or that, this we differentiate, integrate with respect to y. In this case, we integrate with respect to x. The answer should be the same, because we don't change the region. We don't change the region. We just change the order of integral. Okay, so I hope you can understand those things. So that's all for the my second video. Thank you.